Hello student to the wave optics course. So today we have lecture number 20, and in this lecture we will continue the study of interference by division of amplitude. So today we have lecture number 20. And we will continue with the topic that interference due to division of amplitude. So what we had, let me quickly describe in the last class, that if we have a film like this, light ray will fall here and reflect, and one portion is transmitted, then it is reflect from this surface and again it is transmitted. So this is ray 1 and this is ray 2. This ray 1 and ray 2, these two rays will going to interfere, and also we calculate, this is the way the ray will propagate. Also we calculate that if the thickness of the film is T, refractive index is NF, and the refracted angle is theta T, theta I is this angle, incident angle, then what happened, that I can find out the path difference between ray 1 and ray 2, and this path difference is simply 2 of NF T of cos of theta T. That is the path difference we have. Now also we mention that due to the reflection, from the medium N1 to N2, where N2 is greater than N1, we have additional pi phase shift. That leads to a path difference of lambda by 2. So the final condition for maxima and minima, here if I write, so for maxima, that is for constructive interference, we have the path difference 2 nt T, then cos of theta T, plus this additional path that is due to this reflection, which is lambda by 2, is equal to m lambda, or we can write 2 nt and then T cos of theta T is equal to m minus half lambda, just putting lambda this side. Now we can have T into this is not NT, this is NF according to our notation. The refractive index of the film is NF. So this is NF and then T and then cos of no, T is already there, so So it is 2 of n f of t of cos theta. Okay, it is coming. So let me write nf t of cos theta t is equal to it is simply 2m minus 1 lambda by 4, where m is 1, 2, 3, etc. integer numbers. So that is the condition for maxima. For minima, we have 2t nf cos theta t, that is the path difference, plus lambda by 2 is equal to m plus half lambda. So this lambda by 2 will cancel out. So essentially we get this nf t cos of theta t, that will be equal to 2 of m lambda by 4, where m can have the value 0, 1, 2, etc. Here I can have the allow to put the value in m equal to 0. So this is the expression for the condition for minima. So okay, so next quickly I like to show that if we have the interference by extended source, then what should be the setup. So this is interference by an extended source. So what is the meaning of extended source? The extended source means instead of one point source, I have more point source, and say this is S1, this is S2, this is S3, and the ray is coming from this S1, S2, S3, like this parallel ray are coming. And obviously these rays will going to reflect like this, and we may have an arrangement here where we can converge all the ray to some point, but here instead of these rays we have also the reflected ray from this surface, lower surface, which is like this. And it goes like this. So these are the rays that will fall, and it will reflect from the surface like this. Then the transmitted ray will also get reflected by the surface, lower surface, and it will again come here, and suppose this is a lens L, I can put, so here we will going to see the interference pattern. So I can converge all the ray here at some point. This is the point where all the rays are converged by using the lens, and we are going to see a pattern. So here the point P, and maybe we can see a pattern here like this, a fringe pattern like this. This is the fringe pattern one can expect, and this is my film. So this is the way one can find out, or one can understand that how for extended source the interference pattern are formed. In general, we have in the experiments we have extended source, we don't have a point source. So it is important that you should understand the setup through which the fringe patterns are formed in this way. Okay, so after that, after having this setup for extended source, we will understand another thing, and that is called the anti-reflecting coating. So we will make use of this property and try to find out what are the applications and how we can apply that. So our next topic, which is very much related to this concept, is called anti-reflecting coating. So what is the meaning of anti-reflecting coating? That let me describe quickly. This is case 1. When we have a glass placed in air, bare glass, this is air and this is glass, and we have interface here between air and glass. So when the light falls here, it will simply reflect. It will simply reflect, and we can't do anything with this reflection. This will happen. This is simply light reflection. Now we can make this reflection small, or we can make this reflection destructive by putting a coating over that. So this is case 1. In case 2, what we can do, we have a glass, but on top of that we put a thin layer, and then allow the light to pass over this system. And what happened? The light will fall like before here at this point. This is the incident light ray. Then it will reflect from this surface of this coating, and one portion will go back here, and it will reflect again from the glass boundary, hits here, and then it go in this direction. So we have now here 2 rays instead of 1. This is 1 and this is 2 ray because of the placement of this coating. So this is air This is my film or coating material which behaves like a film, and this is my glass. So what is the advantage here compared to the previous case? So in this case, since we have two rays, there is a possibility that we can make these two rays interfere we can make these two rays interfere destructively, and if that is the case, then there will be no reflection out of this system, and that is called the anti-reflecting coating. So the goal here is to put a coat over the glass plate so that there should not be any undesired reflection from this glass block. By just putting a coating, we can do that. So now if we can say that if the reflectivity, if the reflectivity of this, so okay, let us put a name here, A, and this is A prime, and this is B, and this is B prime. So the ray, the reflectivity of AB, the ray AB, which is ray 1, and another ray A prime B prime, which is ray 2, is same, then we can write R1 is equal to R2, which is the coefficient of this reflectivity R1 R2. So for this is for normal, this happens for normal incidence. So suppose the ray is fall normally, so for normal incidence. Then what we have, if we put the refractive index of the air as in A, the coating as NC, and the refractive index of the glass is NG, we can find a relationship between NA, NC and NG. That basically allow us to find out the refractive index of the coating for our desired application. So here for normal incidence we can write NC minus NA divided by NC plus NA is equal to NG minus NC divided by NG plus NC whole square of that. So that is the condition one can get for normal incidence. When we will come to this again maybe in the future lecture. For the time being, my goal is to find out that what should be the refractive index NC in terms of NA and NG by putting certain condition. For normal incidence, if the reflectivity is same, then it is possible that I can write this equation, and this equation is valid here in this case. Now if that is the case, we can manipulate this equation. Let me write down once again because this is another page. So NC minus NA divided by NC plus NA square is equal to Ng minus Nc whole divided by Ng plus Nc. For normal incidence, we can use this expression, which is expression of reflectivity. So, reflectivity from coating to air and reflectivity from glass to coating, we consider these to be same. So, in that case, I can write it. Now, we know that if I write 2 ratio A by B is equal to C by D, then that is equivalent to, these things is equivalent to A minus B by A plus B is equal to C minus D divided by C plus D. That we know. Exploiting this expression, we can find an equation here from this, which is 4 of Nc Na divided by 2 of Nc square plus Na square, and then equal to 4 of Ng Nc divided by 2 of Ng square plus Nc square, just using this identity. We have something like this. So, Nc will cancel out from both the sides, and then if I multiply, and then 2, 4, 4, 2, it will cancel out. So, we have something like Na multiplied by Nc square plus Na square, Nc square plus Ng square, and Ng multiplied by Nc square plus Na square. So, that gives us an expression. If I manipulate this, it should be Nc square. If I take Nc square common and put it this thing here, then it is Na minus Ng, that is equal to Ng Nc Na minus Ng. So, from here I can find the refractive index Nc, which should be Ng root over of Ng multiplied by Na. So, this condition allow us to write down the refractive index of the coating. So, that should be the refractive index. So, first when you put the refractive coating, so this is the structure. We have coating, and then light is falling here, reflected back, transmitted light goes here, then goes here and reflected back, transmitted back. So, this is 1, 2, and this is the way the light is going. This is in air, this is in coating, and this is Ng. So, what we find that if the reflectivity of the Ng and Nc and Nc through Nc and Na are same, under that condition we can find out what should be the refractive index of the coating. And that is root over of Ng Nc. So, that is Ng Na. So that means if we know the refractive index of the glass, we can find out the refractive index of the coating such that this reflectivity will remain same. Now, from this nature we can also find out. So, once we know the refractive index of the coating, we can also find out that what should be the thickness of this coating. So, next the thickness, we need to find out the thickness of anti-reflecting system. So, again anti-reflecting coating thickness. So, for normal incidence, let me draw. So, this is ray 1 and this is ray 2. These two are interfering. This is air, this is coating, and this is glass. And this is the thickness I want to find. And what is the condition? The condition is that ray 1 and ray 2 should be destructive. Then only we can say this is an anti-reflecting coating. So, in A, we figure out that it should be like this. So, in C, the coating refractive index should be in between the refractive index of the air and glass. Now, the path difference is delta equal to 2 of NC multiplied by T, that we already figure. Note that here this ray 1 will be reflected from this point, this interface, and the ray 2 will reflect it from this interface. But in both the cases, the ray 1 and ray 2, the reflection will happen from denser medium to rarer medium. So, that means both the cases there will be a pi phase, and these two basically cancel out. And when it is cancelling out, so here we do not have any phase change or phase shift due to the reflection the effective phase shift due to the reflection will not be there, as NC follows this condition. So, for destructive interference, because it is the anti-reflecting coating, for destructive interference, we can have 2 of NCT is equal to lambda by 2. So, the anti-reflecting coating thickness T should be lambda by 4 NC, where NC we calculate that it should be root over of NG NA. So, here we calculate, through this we calculate that if I use an anti-reflecting coating, then what should be the refractive index of the anti-reflecting coating and what should be the thickness of this anti-reflecting coating. But at the end of the day, what we are trying to find that this is one of the uses that we have for interference problem in under amplitude division under amplitude division interference. So, this due to amplitude division interference, what happened that two ray will interfere, and with this concept it is possible to put an anti-reflecting coating over different systems where we do not require any kind of reflection for different experiment, or in daily life also we want that there should not be any reflection from the glass or any reflective material. Then what we do, that we need to put an anti-reflecting coating in such a way that the desired wavelength for a particular wavelength, what happened that these rays will no longer be reflected because they will interfere in a destructive manner. And in order to put this destructive interference, this we need to put a condition, and that condition we can find out from this interference condition itself, that the thickness of the coating should be lambda divided by 4 NC, where NC is the refractive index, and also we find out that the refractive index of the coating can be figured out easily from the refractive index, knowledge of the refractive index of the air or any other material which is where this glass is placed. So, with that note I would like to conclude today because I do not have much time to discuss more about these things. So, in the next class we are going further. We will going to discuss about the other amplitude division problem, for example the formation of Newton rings, which is a very interesting phenomena, where we can see that whatever the problem we have here, and exploiting this problem we can generate a different kind of structure, a ring kind of structure we can produce. So, with that note let me conclude today's class. Thank you very much for attention and see you in the next class.